This is where we stopped yesterday's class. So we had a look at an example where we had a cache which can hold 4 blocks and 3 different organizations, right? So when we decide the size of the cache, the number of blocks we can hold, we can organize it in different ways. Now, so the first one was direct map, the second one was two-way set associative, the third one was fully associative or four-way set associative. They're the same in this example. So we went through a set of memory accesses, reads coming from the CPU, and after going through each and every access of this list of 5, we ended up with this. The current state of the CPU was this. So in the sorry, not the CPU, the cache, the set 3 caches we looked at were this. So direct mapped cache had 5 misses. All 5 accesses were misses in the direct mapped cache, and we ended up with 2 cache blocks still unused in the cache, right? They're still invalid. Only 2 slots were actually used, but all accesses were misses. So the utilization is not very good, and the hit rate is also not very good in this example. Note that so we had 3 different memory addresses or block addresses in the list here. So 3 of these misses were called misses, like they were compulsory. We couldn't avoid them. First time they were accessed, they are going to be misses. So 3 were called misses or compulsory misses like that, and the rest of them, the other 2 misses were conflict misses. Meaning the data was evicted before they were accessed again. So it became a miss. So that was the direct map cache. And two-way set associative cache, again, the utilization was pretty much the same as the direct map cache. 2 blocks were not utilized, 2 slots were not utilized rather. But we had 1 hit. There were 3 called misses and 1 conflict miss, 1 hit. So a little better hit rate than the two-way set associative cache. And the fully associative cache did not have any conflict misses so far because the cache wasn't full yet, right? So only misses we had in the fully associative cache were called misses. The first time an address is accessed, it was a miss. And the space was utilized well. So we had 4 slots and 3 of them were used for the 3 different memory addresses, block addresses that were referenced by the CPU. Only one slot was unused. So the utilization was high, hit rate was the best we got here. And say when we keep filling these slots, when we keep accessing more and more memory addresses, so these slots get filled eventually, and you sort of go into a steady state, just like in the pipeline. So you sort of experience the cold misses towards the beginning, and towards the end of the program, the cold misses are less, right? The new addresses that are being accessed can be less. Then it's mostly conflict misses that can occur in the cache, right? Okay, so that is what we saw with higher degree of associativity. We were able to get better hit rate, right? With increasing associativity, increasing hit rate. So that is what we wanted. We wanted to improve the hit rate, but at the cost of the hit latency. We need to add more hardware. As we keep incrementing the associativity, you need more and more parallel comparators to decide tag matches. And you need to wait until the intermediate hits in individual ways are determined until you can actually extract the data out of the correct way. So the complexity increases, hit latency increases, and the power consumption also increases because you have more and more logic hardware. But if you want better hit rate, that is one of the good techniques that you have. So better performance also always comes at a cost. So there's as everything, you have to pay something to get something. So you have to trade off your power and cost in order to get better performance. So this is one of the commonly used techniques, associative caches, right? Then we'll talk a little bit about another word, actually, the configuration of a cache. It's another term that we use with caches, the configuration of a cache. So the configuration of a cache has several parameters that we have looked at so far. So one of them is the block size. The block size is the size of a block simply, right? So cache deals in terms of blocks with memory, while the CPU deals in terms of usually words with cache, sometimes bytes, but the conversion between bytes and words are usually handled outside the cache, meaning in the CPU itself. So the term block is introduced with the cache. So the size of a block handled by a cache is one parameter or characteristic of the configuration of a given cache. Then you have the set size. So this is can be a little bit confusing sometimes, but set size here meaning the number of sets you have, right? So in a direct mapped cache, the number of sets are the number of entries. In a fully associative cache, you only have one set, right? So set size is that, the number of sets. And then associativity, as we just learned. So associativity means the number of ways in a set. Number of ways blocks can be stored in a given set, right? So if you take one set, one single set, and you only have one way inside that, that is a direct map cache, right? If you have two different ways in a cache, it's a two-way set associative cache. If you have four ways in a cache, it's a four-way set associative cache, likewise. So associativity refers to the number of ways inside a given set. Set size means the number of sets, number of such sets, right? One set can have multiple ways inside it. Number of such sets is referred to as set size. So it can be a bit confusing, so pay attention to that. Then block size is the size of a single block in bytes. Right, so those three are the key or primary parameters that defines the configuration of a cache. So if you take these three, you can compute the size of the cache. That is the amount of data that can be stored in the cache. So block size, set size, associativity. If you multiply them, you get the size of the cache, right? So then there are other parameters that goes into the configuration, like the replacement policy. When you have to evict a block or throw out an existing block, what is the policy for that? You have least recently used, you have pseudo least recently used, and first in first out. So different, there are other techniques as well. So different replacement policies. So that policy is a characteristic of the cache, so it goes into the configuration. Then the write policy, we discussed write through and write back. There are variants of these policies as well. So write policy is it's another characteristic which defines the configuration of the cache again. And there are other factors, right? So a lot of different other techniques which engineers use to optimize the performance or optimize the power consumption depending on the requirement. So all those other factors also go into the configuration of a cache. So when you fix values or um, say policies for these different parameters, you get a single configuration which defines a particular cache, right? And then the performance or power consumption, everything of that cache is fixed except for everything outside, that is like the memory access pattern coming into the CPU, into the cache and all that. So the term configuration of a cache refers to this. Okay. Right. So then, so far we've been talking about different ways to improve the performance, right? So we had actually three terms in our cache access time equation: hit latency, hit rate, and miss penalty, right? So we tried to see how to improve hit rate. So improving hit rate, the obvious thing or the most intuitive thing that comes into mind is improve the size of the cache, right? So add more slots. So the cache can hold more data, right? So if you can hold more data, more likely you can get hits. So that is the most obvious way to improve the hit rate, but it comes at a high cost. So caches are implemented using SRAM, like cutting edge technology in chip manufacturing, because they need to be really fast. They need to work as fast as a CPU. So they are usually inside the CPU cores themselves. So same technology as used to implement the CPU, so the cost is really high. So you had to decide on a limit, what is the number of bytes for the cache, right? So if you can't keep adding more and more cache space, because the cost is going to be extremely high, and it's not going to be practical to implement such designs. So once you have a fixed size for your cache, once the size is fixed, this is the amount of bytes I can hold in my cache, then other factors come into the picture. So the technique we looked at is set associative caches. So with higher degree of associativity, you get better hit rate. That is what we saw with the examples. You reduce the conflict misses more and more and get better hit rate. So it comes at a range of costs, the cost, like the money cost or chip cost itself, and the power also increases because you have added logic compared to non-associative or direct mapped caches. So added logic compared to direct mapped caches increases our power, increases the cost, as well as increases the hit latency, as we saw when we looked into the design of associative caches. So, but anyway, it is one of the commonly popularly used techniques to improve hit rate, right? Yeah. Then there are various other techniques we can implement to get better hit rate. So one such thing is cache prefetching. Cache prefetching means fetch data before they are needed, right? So it's something like prediction. It's something like the branch prediction you saw in the CPU, right? So if you can successfully predict which data might be used next, then you can reduce the call misses a lot. Call misses or compulsory, they're the same thing. The first time reference misses, you can reduce them only by doing something like cache prefetching. And there are various prefetching mechanisms. You can do it in software, you can do it in hardware, you can do it in both a combination of software and hardware, where the compiler is also involved. A lot of different implementations. We are not going to go into all those details, but if you're interested, I recommend reading a little bit more about cache prefetching mechanisms. So that is one technique or a set of techniques you can use to reduce cold compulsory misses as well as conflict misses by um, fetching certain pieces of data into the cache before the CPU actually asks for them. So um, yeah, so some interesting techniques are available under that topic. So those are the various, some of the various techniques that you can use to improve the hit rate. Primary thing is associativity. Bigger size, of course, is the most intuitive one, but it has a limit. Once that size is decided, the associativity configures the cache. We can configure the cache with the most suitable associativity to get the performance power cost trade-off that you want as a designer, as an engineer. So then other mechanisms, cache prefetching and all that, can be used to improve performance, again at the cost of power cost, because you are adding more and more hardware into the design, right? So right, so the next thing is, so hit rate we saw how to improve, and hit latency is also related to that. So if you try to improve hit rate, you are likely to increase hit latency as well, which is you need to find a balance, right? So if you try to improve or reduce hit latency, then you are likely to affect your hit rate. Hit rate will is likely to also go down. So they are sort of tied together. So the next thing is miss penalty. So miss penalty is usually like largely outside the cache, right? But in the case of a miss, what is the time you need to spend to get that missing block from the memory? So improving miss penalty, um, one thing you can of course do is optimize the communication technology between the cache and the memory, right? So when you have a miss, you have to go to the memory. The cache actually has to send a request to the memory and fetch the missing data. So the communication channels between the cache and the memory, the bus speeds, bus width, bus arbitration technology, and all those different things come into the picture there. So certain optimizations you might be able to do with the communication. We'll not go into detail into that, but can you think of a way to improve the miss penalty of a cache other than the communication? If you can assume that you have the best communication technology, everything is optimized, what might you be able to do to improve the miss penalty of a cache? Can you suggest some ideas? What do you think? What do you think? You can suggest anything. It's okay to be wrong. Don't worry about being wrong. That is what you're here to do, right? You have to make mistakes and learn, so it's fine. Just what do you think? How might you be able to improve miss penalty? Now, for this, you'll have to think outside the box per se, right? So the miss penalty has a lot to do with things outside the cache. So with things that you know, what might you be able to do? Things that you have already learned. How might you be able to reduce the time you spend in the event of a cache miss? By guessing earlier, you're meaning something like the prefetching, like a prefetching mechanism. Are you? Prefetch, guess or predict an access earlier and fetch that before. So you don't you reduce the chance of a miss, right? So that affects the hit rate. That is about what we have in this in this upper side of the slide. So improves the hit rate. Yes, if you can guess, if you can predict accesses before they happen, and you might be able to do that. There are ways to do that. Not 100%, but with good success. So that improves the hit rate. But if you happen to have a miss, if you can't avoid a certain miss, let's say, in the event of a miss, how do we minimize the time we spend to service that miss? If a miss happens, then you need to go and fetch the missing data from the memory, the block you need to go and fetch from the memory. And that time is called the miss penalty. So how might you be able to improve it, reduce that time? Any thoughts? One of the most common ways to do this is adding lower level caches, adding multiple caches, right? So instead of a single cache, have multiple caches in multiple levels. So it's like in our memory hierarchy, within our memory hierarchy, you create a cache hierarchy where in the place where we had a single cache between the CPU and memory, we add multiple caches and create a cache hierarchy itself, right, within the memory hierarchy. So you can do things like that. So I'm pretty sure you have heard terms like level 1 cache, level 2 cache. There are level 3 caches and so on. So the idea is, if we didn't have a level 2 cache, level 1, this top level cache, has to go to the memory in order to fetch a missing block directly. And that consumes a large number of CPU clock cycles. So the idea is, in the event of a missing block in the top level, you fetch it from a next level cache or lower level cache rather than going direct to the memory, right? So the lower level cache can have a reduced miss penalty. It doesn't need to be on a separate chip. It can be on the same chip as a CPU and level 1 cache. But you might use a different technology, and it can be on an off-chip cache, level 2 off-chip as well, right? So that is the idea that you can use to reduce the miss penalty. So reduce the effective miss penalty, right? So for the first level cache, the effective miss penalty is small because most of the misses can be served at the second level. So second level depends on the second level cache's hit rate. But if you can assume a good hit rate here, then most of the first level misses are served at the second level with only a few cycles penalty. If you have a second level miss as well, then you had to fetch from the memory, experiencing the larger miss penalty, the say, 10 to 100 cycle miss penalty. So the second level cache might be would likely be able to supply you with the data within a couple of clock cycles, 2, 3, 4 clock cycles, or even 2, 3 clock cycles is a reasonable assumption. So the average miss penalty or the effective miss penalty for the level 1 cache then becomes the access time of the average access time of the level 2 cache, right? So average access time of the level 2 cache is the hit latency there in level 2 plus the miss rate in level 2 times the miss penalty for level 2, right? So if we can have a good hit rate in level 2, then you can reduce this, minimize this factor, and really reduce the miss penalty experienced by the top level cache. So that is another step you can use to get better performance by reducing the effective miss penalty. So then you can have a question: why not have one big cache if we can do that, right? So earlier we said we first need to decide the size of the cache, then the configuration, right? The size of block size of the number of entries and the associativity within those entries. So to improve the hit rate, so why not combine them together? Any ideas? Why don't we have one big cache? Why do we have two different smaller caches? One small one and one relatively large one as level 2. Why do you think? The idea is when you split the cache into multiple levels like that, you can go for different optimization strategies, right? So if you have two levels like this, top level and bottom level, or top level and last level rather, to use the commonly used terms, you can optimize the top level for hit latency, right? Make the top level cache respond as fast as possible. Get the hit latency down for the top level. So hit latency is the dominating factor, is the key factor that determines the cycle time for the CPU, right? So in the CPU pipeline, the cycle we saw is the the critical cycle is the memory access cycle. That is going to be the slowest latency there, which determines the clock period, right? So your clock period has to be set according to the largest or the slowest stage. So memory access is the slowest stage because of all these things that you're learning, right? So memory has a lot of latencies. So our goal is to reduce that cycle in order to improve the clock frequency for the processor. So if you can improve the hit latency here, then you can reduce the clock period or the clock cycle size for the CPU, which is going to be beneficial overall, right? Can get a better performance from your CPU. And so when you improve the hit latency, you have to compromise the hit rate in the level 1. So in the level 1, we can allow a reasonable hit rate, like, okay, 95% hit rate with the really improved hit latency, really low hit latency, which allows the CPU clock cycle to be reduced. And so the chance of an access being a miss then at the top level is a little higher now, but we go and optimize the low level cache, the next level cache, for hit rate, right? So you optimize the lower level cache to have 99.9 hit rate, really high hit rates. So most of the misses, majority of the misses from the top level are served here at a really low miss penalty. Only a very few misses which happens, like which misses in the top level as well as the next level, has to go to the main memory and experience the bigger 100 cycle type delay. The larger delay is experienced by only a very small fraction, right? So if you have 99.9 times 99.9 hit rate here, and say 3, 4, or 2, 3% miss rate in the top level, then that 2% times 0.01% becomes the fraction of accesses that go percentage of access that go to the main memory, right? So only a very, very small number of accesses go to the main memory, allowing everything to run faster overall, right? So in the event that you have a miss here, the number of clock cycles the CPU has to be stalled is less, because most likely that access is served at the second level cache, right? So the amount of stalled cycles are going to be less, and the size of a cycle is reduced because of the optimized hit latency. So your overall performance is usually improved with technique like this. So you optimize the top level for hit latency, optimize the bottom level for hit rate. So if I ask you a question like that, say if you have two levels of caches like this, which level do you think will have the higher associativity? If you have level 1 and level 2 caches, which level do you think will have the higher level of associativity? Level 2, yes. Yes, level 2 is likely to have higher level of associativity because you implement higher associativity to get better hit rate, right? So with higher associativity, you get higher hit time or higher hit latency as well, but you get a better hit rate. But what we really need at level 2 is better hit rate rather than better hit latency. Hit latency is better hit latency is needed at the level 1. So level 1 caches are likely to be direct mapped or maybe two-way set associative. Not they don't have higher degrees of associativity. Lower level caches or last level caches are likely to be having higher degrees of associativity, like 4-way, 8-way associativity, or even fully associative, depending on the situation. Right. So, right. So that is the idea of using a memory hierarchy. So using a cache hierarchy inside the memory hierarchy to uh, further improve performance by reducing the effective miss penalty. Okay. So do you have any questions on this? Okay. So in real implementations, level 1 cache is usually, not usually, almost always in on chip inside the CPU itself, right? Within the CPU itself, you can find the level 1 cache on a real chip design. And level 2 are usually on chip, but there can be designs where the level 2 cache is off chip, meaning on a different chip. So CPU and level 1 cache are on a single chip, level 2 is on a different chip, and memory on a different chip. So that can be the case as well, depending on the design, depending on the requirement. So if you have level 3, you usually have level 3, especially in multiprocessor systems. They are usually off chip, but there are quite a lot of designs with level 3 is also on chip, especially in multiprocessor system where you have, say, multiple processor cores on the same chip. In those cases, you have level 1 cache per CPU core, then shared level 2 caches, usually one shared level 2 for instruction, one shared level 2 for data, it can be the case, and level 3 shared between instructions and data can be on chip as well. So yeah, different designs have these different implementations. depending on the requirement, what sort of performance you use, you need, what sort of a power budget you have, right? What sort of a cost limit that you have. So depending on various factors, the designs are like this. Okay, so that is pretty much what we had to cover under the topic of caches. So before we go into the next one, I'd like to show you some figures from real implementations. I hope you're still seeing my screen. Are you seeing the screen? Still seeing the screen? So, right. So this website wikicheck.org is a very good site. So I recommend you to go there. Just make a note of that. It's in the lecture slide as well. So I have a lot of details about CPU and memory architectures of real CPUs, right? Various real CPUs. So this one I'm trying to show you is Intel Skylake, which shows the mainstream architecture from around 2015, I think, used in this Core i3, Core i5, i7 processors, the standard desktop or PC computer processors. So I think I have a figure from here. So this is yeah. So this is the actual layout of that CPU, the dual core implementation of that CPU. So you can see here, these are the execution units, right? So this is where you have your ALUs, say, including integer arithmetic logic units, and if you have floating point arithmetic units, multipliers, dividers, all kinds of things are there, right? So you can see two different processor cores you can identify, right? There you can see one, and there you can see the other. Execution units are there. Then a large chunk of the space is allocated to out of order scheduling, branch prediction, all kinds of things that techniques you use to improve the pipeline, right? So multiple issue. I hope you had a look at the extra reading I gave you in the forums. Multiple issues, out of order execution. So the hardware you use to implement those techniques takes up a lot of space, just as much as the execution units in the CPU. Then memory management. So most of control logic are there, decoding logic. Then you can see level 1 data cache, right? So this dollar symbol is to represent cache. It's not cache, but yeah, it's commonly used in these websites to represent. Then you can see level 1 data and level 1 instruction separately, right? So the cache for level 1 data is a separate one there. Level 1 instruction is separate. The instruction is, you can see level 1 instruction cache is sort of located closer to the decoding and out of order scheduling, all those, say, units, hardware that deals with the instructions, right? Fetching of instructions. So they are located close by, or in sequence rather. Then the level 1 data caches are located rather closer to the memory management and execution units, where the addresses are coming from the execution unit, and the memory management deals with various things that you have to, you can do, techniques that you implement when sending requests to the memory. And the level 2 cache, you can see there is, it's bigger and it's shared. So these level 1 caches are most likely optimized to get better hit latencies. So your pipeline cycles are reduced. cycle time are reduced. So then you have level 2 likely to be optimized with higher degree of associativity to get really high hit rate. So the effective miss penalty is reduced. So the number of cycles the CPUs have to stall in the case of level 1 misses are low. Somebody's raising their hand. If you have a question, you can ask. Oh, you're still seeing. Okay. Sorry. um, I'll stop this share and share again. So what you see here is the dual core implementation of this Intel Skylake architecture that is used in this Core i3, i5, i7 CPUs. I think from 2015-ish, that was when it was first introduced. So, but the layouts are similar in most other designs as well. So we can see the execution units here, which contain things like your integer arithmetic units, multipliers, dividers, floating point units, and all those things there, right? And then level 1 data cache, memory management and execution related hardware, control hardware in the center, and level 2 data cache, level 2 shared cache for instruction and data there. It's a bigger one. And level 1 instruction cache, right? You can see a slightly different configuration compared to the data, right? The arrays you can see, block arrays. If you like carefully zoom into it, you can go to this website and look at it. Then you see decoding related hardware here and instruction fetching related hardware for say things like out of order execution and branch prediction, uh, multiple issue, right? Different techniques. So look at those techniques. I shared some material in the forum, so have a look at them. So you can see that a lot of hardware are allocated for those techniques to get better performance at the end of the day, right? And level 1 cache, instruction cache is located closer to this decoding, instruction fetching hardware, right? As you can expect. And data cache is located closer to execution units where the address is coming from, and other memory management hardware. Level 2 is here in the corner, closer to level 1 and level 1 data and level 1 data and instruction caches. Shared level 2 is located closer and it's bigger, right? So it's most likely to be implemented using higher degree of associativity. So you can try and figure out the associativity by looking at the diagrams if you want. But yeah, so then if you can you see this other diagram I'm showing you now? I changed the slide. Can you see? Yeah. Tab. Yeah. Okay. So right here, what you're seeing is the block diagram for the same thing that we saw earlier. So you can see the execution units are here, right? So integer, ALU, divider, multipliers, shifting units, whatnot, right? Or floating point units, all kinds of things you can see there. Then your data cache, level 1 data cache is here located closer to your execution units, and you can see some buffering is used before the cache, right? Even before the cache, in between the CPU and the cache there are some buffering used for store instructions separately and load instructions separately, right? We talked about buffers being used after the cache, before the memory write buffers, right? So there you can use buffers even before the cache. So the level 2 shared cache, the large one, 256 kilobyte one, 4-way set associative here, is there. Actually, this one is 8-way associative level 1, so it's a bit off the logic that we discussed, but the size is smaller, very smaller, so compared to the level 2. So having a higher degree of associativity might not impact the hit latency that much, right? So remember, it all depends on the clock cycle, clock period. So there are a lot of other hardware in the CPU which affects other stages of the pipeline. So there might be a limit. There will be a limit. You can reduce the cycle time using the caches, right? So the hit latency after a certain improvement, you might not be able to improve further because other factor in the CPU becomes the bottleneck, right? So it can be the case, but the usual logic is higher degree of associativity gives you high hit latency, but that depends on the size as well. So if you scroll up, you can find a lot of other hardware with this instruction cache, level 1 instruction cache up there, instruction fetching and pre-decoding mechanisms, branch prediction, out of forward execution, hardware used for those things, a lot of hardware related to instruction fetching, right? So that is what you saw in the real layout as well. Then register file, physical integer register file and vector register file, and so more complicated implementation because of course it's a complicated CPU x86. But yeah, you can see the things that we talked about here, right? So right, and then this is a single core of the CPU, and it connects to level 3 cache through a bus there, right? So when you can have multiple such CPUs on the same chip along with the level 3 caches, that is the implementation of Intel x86 Skylake architecture from a few years ago. Right. Okay. So I think I'll stop here now. You can go to this website, webkeychip.org, and have a look at different architectures. I think some ARM implementations are also shown there. So it'll be a good exercise for you to see how these things are actually there in real implementations, the concepts that we talked about. Right. Okay. So we'll stop here. We'll start the next lab and the next topic in the lectures also next week. In the lectures, next thing we'll be talking about is virtual memory, which also needs hardware support. So we'll talk about that from next week, and we'll start your lab 6 next week, where you will be implementing cache memories and adding memory modules to your CPU, which you built in lab 5. Okay, right. So we'll stop here.